In this lesson, we're going to focus on the basics of acids and bases. So one of the first things that you need to be able to do is you need to be able to identify an acid or a base if you're given the chemical formula of it. Acids typically have a hydrogen in front of them. So HCl, that's hydrochloric acid, HF, hydrofluoric acid. As you can see, there's a hydrogen in front of it, or acetic acid, HC2H3OH. Those are acids. Bases typically have a hydroxide ion, like NaOH, KOH. Those are bases. If you see a hydrogen next to a metal, like sodium hydride, then it's a base, not an acid. But if the hydrogen is attached to a nonmetal, typically it's an acid. So whenever hydrogen has a positive charge, it's an acid. But if the hydrogen has like a negative charge, then it's a base. Acids tend to be positively charged. Bases are usually negatively charged. Now you need to understand the Arrhenius or Arrhenius definition of acids. Acids are basically they're substances that release H plus ions into the solution. Hydrogen ions are equivalent to hydronium ions in water. This really doesn't exist by itself in water. In fact, it's actually bonded to water, and so it exists as H3O+. The Arrhenius definition of bases is that a base releases hydroxide ions into solutions, while acids, they release H plus ions into solution. So keep that in mind. Now you also need to know the Bronsted-Lowry definition of acids. Acids are proton donors. Bases are proton acceptors. So let's say if we put hydrochloric acid in water, what's going to happen? HCl is the Bronsted-Lowry acid. H2O is the Bronsted-Lowry base. The acid is a proton donor, so HCl is going to lose the hydrogen and turn into chloride. The base is a proton acceptor. Water is going to accept the H plus ion and it's going to convert into the hydronium ion. This is called the conjugate acid because we added a hydrogen to water to make it, and this is the conjugate base because we took away a hydrogen to make it. So the acid always turns into the conjugate base, and the base turns into the conjugate acid in the course of an acid-base reaction. Let's look at another example. Ammonia, when it reacts with water, it produces NH4 plus and OH minus. In this example, identify the acid, the base, the conjugate acid, and the conjugate base. So notice that NH3, it gained a hydrogen, turning into NH4. So therefore, it's the proton acceptor, which means NH3 is the base in this example. Water lost the hydrogen. So water was the proton donor. It gave away a hydrogen, which makes it the acid. Now the base is always going to turn into the conjugate acid because we added a hydrogen to it. So NH4 plus is the conjugate acid, which means hydroxide has to be the conjugate base because water lost the hydrogen to make it. Now let's say if you're given water and you want to write the conjugate acid of water and at the same time the conjugate base. What is the conjugate acid of water? Whenever you want to find the conjugate acid of something, all you need to do is add H plus to it. So you're going to add a hydrogen and increase the charge by 1. So this is going to turn into H3O plus. The charge increases from 0 to 1. Now, whenever you want to write the conjugate base of something, take away a hydrogen and decrease the charge by 1. So instead of having 2 hydrogens, we now have 1, and the charge is going to decrease from 0 to -1. So the conjugate base of water is hydroxide. The conjugate acid is H3O+. So given ammonia, write the conjugate acid and the conjugate base of NH3. So the conjugate acid, we got to add a hydrogen. It's NH4 with a plus charge. To write the conjugate base, we need to remove a hydrogen, so it's NH2 with a negative charge. Now, for the sake of practice, try this one too. Let's say we have H2PO4-. Write the conjugate acid and the conjugate base. So we got to add a hydrogen. This will turn into H3PO4. So that's the conjugate acid of this thing. The conjugate base, we got to take a hydrogen and then decrease the charge by 1. -1 minus 1, that's -2. So now you know how to identify and how to write the conjugate acid and conjugate base of a substance. Now let's talk about the pH scale. I probably should have went over this earlier, but better late than never. So typically in most textbooks, you'll see the pH scale between 0 and 14. However, it can go beyond those numbers, so keep that in mind. At 7, the solution is neutral. At a pH that's less than 7, it's acidic. So if the pH was -2, it's very, very acidic. Above 7, the solution is basic. Now, if you want to calculate the pH of the solution, you need to know the concentration of the hydronium ion, or the H+ ions. It's negative log of H3O+. And the pOH of the solution, it's negative log of the hydroxide concentration. The pH plus the pOH always adds up to 14 at 25 degrees Celsius. Now, for some reason, if you ever need to find the H3O+ concentration, it's 10 to the negative pH. And if you need to find the hydroxide concentration, it's 10 raised to the negative pOH. So those are some equations that you might find useful when learning about acids and bases. Now, let's talk about strong acids and weak acids. You need to identify if an acid is going to be strong or if it's going to be weak. Strong acids ionizes completely. Weak acids, they partially ionize. They don't ionize completely. So a strong acid, basically, almost all of it would ionize in solution. A weak acid, less than 5%. Strong acids form strong electrolytes in water. The solution will conduct electricity. Weak acids form weak electrolytes when dissolved in water. So you need to know the 6 most common strong acids, and these are HCl, HBr, HI. HF is a weak acid. The others are nitric acid, HNO3, sulfuric acid, H2SO4, and perchloric acid, HClO4. Those are the most common strong acids that you'll see in a typical general chemistry course. Now, other weak acids include the ammonium ion, NH4+, acetic acid, and basically almost any acid that is not on this list. So like cyanic acid, nitrous acid, and sulfuric acid. Notice that sulfuric acid is stronger than sulfuric acid, and nitric acid is stronger than nitrous acid. What pattern do you see here? When dealing with oxyacids, the acid that has more oxygen atoms is the one that's going to be more acidic. So sulfuric acid is more acidic than sulfuric acid, and nitric acid is more acidic than nitrous acid. Perchloric acid is more acidic than chloric acid, which is more acidic than chlorous acid, and that is more acidic than hypochlorous acid. Now, HCl is not an oxyacid, so it doesn't fit this trend. In fact, HCl is more acidic than HClO, so keep that in mind. The trend only works for those that actually have oxygen. If it doesn't have oxygen, it's not going to fit the trend nicely. Now, you need to know how to write chemical reactions with strong acids and weak acids. We went over the example with HCl and water. Because HCl is a strong acid, it ionizes completely into chloride and hydronium ions. So notice that I have a single arrow. So that's the way you need to write the chemical reaction if you're mixing a strong acid in water. Now, if you're mixing a weak acid with water, it doesn't ionize completely. So you have a reversible reaction. So you need to use a double arrow symbol rather than a single arrow whenever you have a weak acid. But to identify the products, it's going to be very similar to the reaction above. So the only difference is just use a double arrow instead of a single arrow when dealing with weak acids because they exist in equilibrium. The reaction is reversible. Now let's talk about bases. You need to identify or distinguish a strong base from a weak base. Strong bases are soluble ionic compounds like potassium hydroxide, sodium hydroxide, barium hydroxide. These are soluble in water. They ionize virtually completely. Think of the strong acids like HCl, HBr, HI. The reason why they're strong is because they ionize almost 100%. So these are soluble, and as a result, they form strong electrolytes. And so they make strong bases. A weak base, the ones that have hydroxide in them, they're associated with insoluble compounds. Aluminum hydroxide doesn't dissolve very well in water. Only a small amount of it dissolves. And so it's insoluble. And it doesn't ionize. It ionizes less than 1%, which makes it a weak base. So I'm going to put here 100% ionization, less than 5% ionization. Some other examples of weak bases include ammonia and the conjugate bases of weak acids like fluoride, nitrite, acetate, cyanide. All of these are weak bases. Even HSO3-. Other examples of strong bases besides hydroxide are oxide. If you have oxide in solution, that's a strong base, and hydride. If you put an oxide ion in water, it's going to grab a hydrogen from water, creating two hydroxide ions. So oxide is a stronger base than hydroxide because it has less hydrogens. Hydroxide is a stronger base than water. Water is neutral. And water is a stronger base than H3O+ because H3O+ is acidic. So as you can see, the less hydrogens that are on an atom, the more basic it is. So oxide is more basic than everything else in this list, whereas H3O+ is most acidic. Hydride is also a strong base. When it reacts with water, it's going to produce hydrogen gas and hydroxide. So notice that hydride produces hydroxide. Typically, a stronger base will produce a weaker base, so hydride is a much stronger base than hydroxide. Let's talk about the mechanisms of these reactions. So this is oxide. It's basically an oxygen atom with 4 lone pairs. And I'm going to draw the Lewis structure of water. This oxygen has 2 lone pairs. So oxide is going to use one of its lone pairs to take a hydrogen atom from water. The arrow represents the flow of electrons. So this arrow tells us that this lone pair is going to be used to form a bond between the oxygen atom and the hydrogen atom. When the hydrogen atom breaks away from water, the two electrons in this bond is going to go back to the water, which is now going to be hydroxide. So this oxygen gained hydrogen, so now it looks like this. It lost a lone pair, so instead of having 4 lone pairs, it now has 3. And it no longer has a -2 charge, but it has a -1 charge. Now this oxygen, it lost a hydrogen, so now it has 1, but it gained a lone pair, as indicated by this red arrow. So now it has a -1 charge. So as you can see, whenever you mix oxide in water, if it's not bonded to anything, it's going to produce 2 hydroxide ions. Now let's consider this reaction where we said hydride plus water produces hydrogen gas and a hydroxide ion. So hydride is basically a hydrogen atom with a lone pair. So it's an ion in this case, and it's going to react with water. Now the hydride ion is attracted to this hydrogen, and the reason why it's attracted to it is because that hydrogen has a partial positive charge. It's partially positive because it's attached to a partially negative oxygen atom. Oxygen is electronegative, and as a result it pulls electrons towards itself. So as it pulls electrons towards itself, it leaves a partial positive charge on the hydrogen. And we know that opposites attract, so this hydrogen ion with a negative charge is attracted to this hydrogen atom with the partial positive charge. So those two will connect. And once they get together, this bond is going to break. Those 2 electrons are going to go back to this oxygen. So when these two get together, they form hydrogen gas, H2, leaving behind a hydroxide ion. So now this oxygen now has 3 lone pairs instead of 2. And so that's the mechanism for this reaction. So whenever you add hydride or oxide to water, it causes the solution to become basic. It produces hydroxide ions.